All right. Let me probably need this. Okay, very good. So people online, can you hear me?
Yes.
I can hear you.
Thank you. So let's start with project 1 solution and the grading, because the project 2 is already available and you have only 2 weeks to work on it. So I think you should be comfortable with the way we are grading the project. Saqib is grading the project. Okay, and so the whole idea behind this is to prepare you for the actual capstone project at the end. So this is actually a small version. This is supposed to be a simple version. So I am really surprised with how some of you say that it was so much, and also the confusion, the amount of questions that people asked that seemed that they were not really aware of like how small this project was. This was not a big project. Okay. Yes, 5% of the course project, but it was not really that big. So first, the grading, and whether it's fair or not. So we grade every task on a scale 1, 2, 3 to 4. If you don't do it, you should get 1. So no one should get 0 in any one of those 5 tasks. So if you submit any stuff, you should get 1, 1, 1, 1. Okay, so that's 25%. And you don't pass because passing is 50%. That's fair. You didn't do anything. We give you 25% just to acknowledge you exist, right? But you are not gonna pass. If you did every single thing wrong, every single task is wrong, you get what? You get 2, 2, 2, 2. That's 50%. You still don't pass. The passing grade is 55%. So we give you 2, 2, 2 in every single task just to acknowledge you don't just exist, you actually try, but you don't get it. You shouldn't leave this college. You're staying with us. That's fair, right? You didn't do it right and you get 50% and you don't graduate. You stay with us. Okay, 1 more year. Now, if you do everything right, you should get 4 and you are our A student. If the student that do everything correctly, we acknowledge that this is our top caliber student, right? And people should hire you with our blessing. That makes sense. Now it's the 3. The 3 is when you do something wrong. And so that's when all the fighting will happen between you and the grading and between you and me. So there are 2 levels of fighting over that 3. So if you didn't, if you did the trial but the TA didn't see it, you talk to him immediately. You tell him, like, why did I lose 3 on task 2? I did what the professor said, or I did, what the problem is asking me. You get immediately 4. The second level of argument is that, yes, I didn't do it right, but it's not a big deal. Why did I get 3? I should get 3.5. And that is a little bit subjective. Is that too close to be a 4 or not? It's really a 3. That's when and he could convince you. And if you are not convinced with what he said, then you can come to. Right? But this I think the grading is so simple. I think one time one of the students wrote in the course review, we should actually do like an intermediate review too, so that you tell me if anything is wrong so that we can fix it before the end. But one time, one of the students commented that the grading scheme is so simple, we could grade for ourselves. We don't need anyone to tell us we did it wrong or we did it right. We can grade for ourselves. So that should be the case. And if it's not, tell me, and we can simplify things. So now maybe what's not really clear is what is expected for each task. So let's go through them while we are looking at that solution so that we also can prepare for the second project, right? So the first part is the problem statement. The problem statement, it is a statement, but I'm expecting a number. I'm expecting my number. The number that I give you in the problem, I want you to rewrite them for me. But maybe in like, you know, one line per number. You would say goal or what's required is designing a power plant with the following. He said output should be this much. Maximum temperature should be this much. Condenser temperature, you are relisting what was given to you. Nothing more, nothing less. But I need to see numbers, right? You cannot just say, if the problem statement is we care about the environment and we'd like to reduce CO2, and one way to do this is to have clean, efficient power plant. Where is the number? Where is my 1,000 degree, right? So problem statement was what the customer is giving to you. Okay? You do this right, you say what's given and what's required. What's given and what's required. You also required is, maybe I didn't write here what's required, but please, it's like please design, I guess that's what's required. Design a heat stage and an oil feed water stage and optimizing the solution. That's basic tasks 3 and 4. Right? Is that clear? Everyone understand? Task 1 is rewriting the problem that was given to you, but in rather than a big speech like this kind of a speech. We don't like that as engineer. We like to see 1, 2, 3, 4. He gave me those, he's asking for these. Okay? And that is the case in the midterm too. That's coming soon, right? I'd like to say, you know, I like you to rewrite what I give to you in the exam. Then it's just, what would be nicer too is this with a symbol. So rather than require power output, you would say what? Huh? Excellent. WorkNet. See, just writing WorkNet and actually work.net. Work.net, then you're already in the back of your mind preparing the scheme for the solution. You're saying WorkNet, that's what? That's turbine minus pump. I better get my work pump and my work turbine. And then I'm going to subtract and give him his WorkNet. Right? So I'm expecting in the exam, I'm expecting also symbol. Right? So maybe here maximum temperature, I would say T1. So that already tell you, we start the cycle from the top, that's T1, and then we go 2, 3, and 4, right? So that would be nice. And also units, like here, it's okay to list it like this, but my recommendation is not required. But my recommendation in the midterm is to turn everything into SI. That's not okay. Megawatts not okay. You immediately try it 512 times 10 to the power 6 watt. This guy, I mean, we are leaving it like this because it's like what industry usually use, but you're gonna use steam table or gonna use steam and he use degree C, so maybe you convert to what you're gonna use. You got my point. Task 1 is the easiest, right? And still I saw people not getting 4 in task 1, surprisingly. All right, so task 2 is the number that was not given to you. 1 is the number that was given to you. Here is the number. 2 is the rest of the number, the rest of the constraint that should have been said, but it was not. So for example, if I didn't say this was isentropic or ideal cycle, somewhere here, he said, I hope. Did we say isentropic somewhere? Ideal steam power plant. Consider an ideal steam power plant, right? So if this was not given, well, what is the efficiency of the pump and the turbine? So here in 2, you would say, assuming isentropic efficiency turbine this much. Why? Because the SME standard said that, or because I found the paper that said that. You are pulling more numbers from experience, from standards, right? And that is the part that people struggle with in the senior design? Huh? And that's kind of the question that when people ask me, I don't reply. When we say, well, what pressure should we use? If I tell you that become a homework problem, if I give you every single thing, you just fill in the plane and get the number, that's a homework problem. So what's hard about this course is that I don't give all the number. I need you to come up with the number. And yes, it's challenging at the beginning. Like, I have no idea what is the pressure of a power plant. I'm still a student. I don't know what is it. I didn't visit power plants. I didn't work as a consultant. I have no idea. That's when you gain that experience by Googling, looking at the homework that we had where there was actual big power plant and you saw the number. That's a good starting point. I could start with what they had in Jenks. They had what, like 3,500 PSI absolute? Coming back from the turbine and going was like 4,000 or something. You could start with those numbers. Okay. So here, I didn't expect, like, I saw people writing a full page of a lot of things about power plant. I just need a bunch of numbers, specifically numbers that are useful for this problem. So I think maybe the maximum pressure that we limit our design. I mean, we cannot go to infinity. You wish, but the pipes cannot take it. There is a limit to the material, right? When we expand to the turbine, obviously as I go up, right, that X2, the X of turbine will go more wet. So there must be a limit to how wet can the X of turbine be. And we talked about this, and I told you how I felt when I put my hand on the turbine plates in the Jenks power plant and how I felt really sorry and how that was so sad. And right, remember that? It wasn't a joke. I really genuinely felt sad for that turbine. Like, I really feel for it, you know? So my point is, there are numbers that you need through the solution, and you will discover them through the solution. Like when you are doing task 3, you're like, what is the minimum X2 that I should allow? Or how high in task 1, how high does he want me to go? And then you search and you find numbers. Then you put them in task 2 as part of, here is my design domain. I'm gonna bound my design domain, but by this, right? Make sense? Everything clear about task 2? 1, number was given to us. 2, the number that we need to solve the problem. We need to supply. Okay? You get 4. You put number, you get 4. Right? Very good. So now task 3, that's really like a regular homework problem. Once you know what are the constraints, he's basically saying consider 3 design, right? 1 that's ideal, Rankine cycle was super critical. This, what we call this the critical point. Super critical means we have to be above it. The pressure need to be from this point upward. This point is what? How much? 220, kind of? 220. So 220 up to the maximum that you're gonna cap yourself at. And in that range, that would be a supercritical. If the pressure is there, that's a supercritical. And we said in task 3, someone got confused and he said, or she said, we need to optimize every one of those. No, in task 3, just like in the second project. So in the second project, we're gonna design a heat pump, a vapor compression cycle. Okay, and I'm telling you on task 3, please consider 3 different refrigerants. Okay, so 3 different refrigerants. Not optimizing it, just pick an operating pressure, you think it's okay, and calculate the COP. This is done not just to make your life easy. No, this is actually the point behind that I didn't come up with that project structure, by the way. It's like a bunch of professors. So when we were trying to evaluate like different objectives of our program, they divide us into a bunch of groups, and every group of professor was tasked with coming up with a good evaluation criteria for each one of those activities. Experiments, presentations, right? And so the group that was tasked was how we can design how we can evaluate a project, a design project. They came up with this task 1, 2, 3, 4, and 5. And so the point behind task 3 is, this is important for your capstone too. The point behind task 3 is to tell you that you can come up with a very quick answer, and we will see right now, not far away from the full answer that will take 2 months of calculation, but you can come up with a very good answer very quickly by simplifying things. Okay? And so it's really important that you come up with those like 3 alternative design with the simplest way ever. But that simplest way, there's an art in coming up with that simple way, right? So like here, the simple way of this is assume isentropic. Yeah, it's not isentropic in real life, but it's not that bad. But can I assume that, for example, that temperature is 10,000? No, it still need to be realistic, right? Is isentropic is realistic? No, it's not. But will I be totally wrong if I assume isentropic? We will see right now. Surprisingly, this simple design will come up with a number that is very similar to what you will get from the big power plant in Jenks with so many feed water heat. By saying same number, I mean the same order of magnitude. Like, for example, the flow rate that will come is like here, is going to be 3 point, or like 2.9 or something, million pound per hour. What is the actual mass flow rate from the complicated cycle with so many feed water heater? 3.5. Yes, 2.9 is not the same as 3.5, but I got the 2.9 million pound per hour. So I'm ready to head basically the purchasing team in our company and tell them, guys, find out who sell pumps that can handle 3 million pound per hour, because my 5 minutes calculation show me we are gonna go 2.9 million. Means gonna go real number is 3.5, but 2.9 million pound tell you the right order, right? We can start thinking about the pipe diameters that will handle that flow rate. Who would sell them? Figure out if they are available this summer to supply those things for us. So those speed calculations are very useful, huh? And yes, they don't get you 100%, but at that stage, if you give me what is 2.9 divided by minus 3.5 divided by 3.5, I would say if we get 75% of the results, that's pretty good. In 5 minutes calculation, you will be treated like a hero in the team. You're like, wow, this guy, he has magic. He probably do some black magic or something, because like you just look to the sky and then he tell you 75% of the answer. Okay. So in task 3, we don't optimize. We just pick one realistic test condition and we calculate the stuff. So he said, for each one of those guys, plot on TS, actual TS, and sketch the cycle, that's the sketch, right? And calculate the thermal efficiency and the mass flow rate in the turbine. Okay, so this would be the sketch, but of course, a better sketch would be on the actual, thingy like this. Okay, and one thing that you need to notice that, and we talked about this in the class, see all those pressure, they all collapse to here. So where do they exist? They exist between the blue line and the red line. All of them exist between the blue and the red. So when you guys come here at the pump and you go up like this to this point and you draw a line, that is wrong. I don't think the TA took points, but I would if I was grading, right? Because it make you show up as if you don't really know what are you looking at. So they will plot the pressure like this, and then they will go like this, and then say this is the feed water heater, and this is second pump, and then they will go like this. That's not okay. So how can I plot it? Well, in real life, and there's a point why I told you to plot it on actual phase diagram, because that cartoon that we always do make people think that the pump work is really significant. But in real life, where is the pump work? The whole thing is here. Before the pump and after the pump, it's just like this dot. Compared to what? Compared to this, which is the turbine, right? So it makes you realize the scale of things. Good? So all we wanted is ouch, right here. That sketch on the TS diagram, right? This guy and the equation, right? And the equation, he wants the eta thermal. Where is the beef? Where is the equation that will give me eta? Work over Q. And what's work? Work net. This guy minus this guy. And that's the Q, right? And how much is the m dot? How do I get this? Power equal m dot net. And you get the number between them. Okay? Question about this? So that is like a homework problem. How is that too long? That's pretty easy, right? Yes? The second one, let's see what this. The second one is with the reheat. And we didn't say whether the heat need to be 1,000 or not, right? So this would be part of number 2, right? In task 2, you will probably have to say that I'm gonna cap myself as 1,000. Chances are the heater will get the same temperature like the first superheater because they are both sitting in the boiler looking at the flame. You are in camping, you have wood in the middle, you are sitting here, your friend is sitting there looking at the fire. You probably will get the same heating, right? Because you are looking at the flame from the same distance, right? You can assume this. I lied. In real life, no, superheater is first, then the heater second. But I mean, they are very close to the flame, right? But again, this is our assumption. We are doing a design here. So we can just assume for now the heater is also gonna hit 1,000. Very good. So you come down like this, and then you go up to the same temperature. That's how the cycle will look like. And that's the sketch. And same equation, right? And all those equations are in the heat cycle, the ideal cycle. Where are those equations? In the lecture notes from the book, right? You just open the PDF, you will find this equation. So they are not really any surprise, right? So work net is got 2 turbines, right? Minus the pump, and you got 2 heating. That's the part that sometimes people do forget. The heating is 2 parts, from 6 to 1, and then from 2 to 3. Make sense? From 1 to 6, and then from 2 to 3. And same thing for work net, equal m dot times specific work, you can get your m dot. Those property, you can get them from the steam table, you can get them from Xteam. In part 3, then you don't have to use Xteam, but you can just use it to get the property if you want the edge. Or you can open the steam table in your thermodynamic book if you still have it, or you can, this is a really good site, and I put this link in our canvas. This is that produce energy. They have a steam system modular tool, and they have a bunch of other stuff too for boiler and the aerator. That's the open feed water heater. That's what they call the aerator. Steam turbine, you can play with those things. Those are very useful. Okay, so you put the property, and he will read for you the enthalpy, the entropy, tell you whether it's wet or dry, and what's the split volume? What's that? New. Okay. So we can get the property from there. And finally, the feed water heater. Okay, so in the feed water heater, they take some of the steam at state 2 at a certain pressure. You were trying to find it in task 4 if you choose this. So they take some of the steam, m.2, and they heat the rest of the flow. What's the rest of the flow now? m.1 minus m.2, right? So this m.1 minus m.2 that's coming at 5 now will get heated from 5 to 6 by the steam coming from 2 to 6. This is actually very important for the quiz today. If you are looking at your cell phone, leave your cell phone and look up to me, because this part is important for your quiz today. When we have an open feed water heater, the exit is 1 point. 5 and 2 come together and leave at 1 point. After the open feed water heater, they basically get pumped to the next pressure, which is the boiler pressure. Okay, this is different from closed feeder water heater. So in today's quiz, there will be a bunch of open feed water heater and closed feed water heater. And so it's important to know how we can sketch and understand the two of them. Okay, so if this is the turbine expansion, and here is a compressor, so the condenser, and so here is your pump. That's how an open feed water heater works. So if this is 1, 2, and 3, 2 will be coming like this, 3, 4, 5, 6. 5 will come here, and then 6 will be leaving here. There will be another pump that take you to, say, 7, and then 7 will get into the boiler so that it can go all the way up to 1. See that part? I would like you to understand this part. Yes. Is 5 and 2, and that's excellent. For open feed water heater, yes, because this is one room where things get collected air. So if 5 was not high enough, it will not be able to go to that tank. And that's the point of this pump. There's another pump here. There's another pump before that will take you from 4 to 5. Okay. Now this is different from a closed feed water heater. Right? So a closed feed water heater, just like the one we did the homework on, the steam go around the pipes. So the water is coming, say, from 5 to 6, while the steam 2 is condensing on the pipe. For him, those pipes are so cold. So he will condense and become liquid, and he would leave. Okay, so if I plot this on a TS diagram, so here is 1, and here is, we're going to extract 2 here. Okay, And
I
here
don't think
is
we can
3,
see this online.
4, 5. Okay, now this 5 is coming from a pump that can pump it all the way. This 5 could actually be the boiler pressure. Okay.
We can't
And
see the screen.
you cannot see my screen.
No.
How is that possible?
Oh, no. Yep, so now.
Okay. You can see it now, right? Actually, it's retarded, like it's behind. Let me stop share and then share again. Let's see if it's all right. How about now?
Yeah, that's good.
Okay, so at this I'm trying to plot the closed feed water heater. And I'm saying that in the closed feed water heater, the pipe is not open. That's why they call it closed feed water heater. The pipes send the water from 5 to say something like, this is horrible. Let's reduce the pen font. Let's plot the descents. Yes, there you go. So pump is expanding from 1, 2, 3, condenses to 4, it bump it up to 5, and then 5 is the boiler pressure. So in the boiler, the water will go all the way to hit 1. Okay, so now to help the boiler a little bit, we are using this guy, the closed feed water heater. So he's saying, well, 5 is so cold, let me heat it a little bit. So he's heating it to 6. How he's doing this? By using steam from here, from 2. And as the steam cool down and heat the water, he will go from 2 to 7. Okay, and the question now, what do we do with that 7? So we have 2 routes for 7. We can cascade it backward. We put a pressure trap because like his pressure is high, a throttling, and we send him to the lowest place where they need heat. What's the lowest place? Let's dump it to the condenser. If there was another feed water heater, if there was like a bunch of series of them, like for example, there's another feed water heater over here that's pulling from say 0.7 or something, or 8. Here's 0.8. He's like this. This guy, after he does his job and he heat the water from 6 to say 13 over here, what do we do with that, with his steam? We dump it to the next feed water heater. Valve over here, and you dump it in here. So this is called cascaded backward. You are taking the steam after he finishes his job and become liquid. Yes, he's liquid. Yes, he does not have huge edge. This edge was so big. But this edge, yes, it's small, but he's still what? He's still hotter than you. Yes, he have only 100 joule per kilogram, not 2,000 that he used to have over on this side. But I mean, those 100 joule are available, and he's hotter than you. You can get him. So that's why we throttle him. And throttling go down like this. Okay, you go to the previous level. Okay, that is the simplest way to do it. You got me? So if you want to plot a feed water, a closed feed water heater, you notice how 6 and this are different. Does this make sense? The temperature of the existing feed water the exiting temperature of the feed water and the condensing steam 7, which one of them should be higher, 7 or 6? Which one should be higher? 7, because 7 is the one that's heating 6. So 6 need to be a little bit lower. And that difference between 7 and 6, anytime you heat something by someone else, you need to be hotter than that. That is called the terminal temperature difference. And that is of order like 5 degrees, 3 degrees, right? So now for a free quiz, you don't have to solve today's quiz, okay? And by the way, today's quiz is annoying in the fact that the attendance is only 20%, but the actual quiz is 80%. So it's a big deal if you get a free quiz. I mean, it's really valuable. So what is a free quiz? How? So I understand the terminal temperature difference is like 3 degrees, 5 degrees, because you need the temperature to heat with, right? I mean, ideally, it could be 0, ideally speaking, right? In the perfect world, it could be 0. But explain to me how it could be, how the terminal temperature difference could actually be negative 5 degrees. How is that possible? And this is also for online people. How could the terminal temperature difference between the exit water and the condensing steam could be -5? Like how the water is hotter than the actual condensing steam? Anyone? Six is hotter than 7 by 5 degrees. How is that possible? Can't hear. Different? No, this is just steam. This is the same cycle.
Is it if the steam flow rate is higher than the water?
No. So the answer, who said that? Robert?
Yeah.
Robert saying, well, what if you control the flow rate such that, you know, one guy is like moving very slowly and the other one is like a lot? Well, no, ideally, even if this is the case, you still get 0. You don't get negative. So what's your name? Jake is saying maybe it's unsteady operation, like you are in a part where things were recycled or something. No, I'm talking about steady state operation. How in steady state operation, things will be such that 6 is hotter than the condensing steam that's heating it. Okay, I'm gonna get my free quiz. My free quiz is answered by this. You are thinking about this temperature. That's the definition of temperature difference. But this is the actual inlet. So they designed the feed water heater such that when the steam come in really hot at 8, that's basically his point. He go into a section like this. They call it the D superheater. This is a place where the steam lose is this guy, and then he start going to the, from this point onward, he become a T saturation. But in this place, he lose the desaturation, okay? And the pipes are such that they are actually going this way. So the water, after it come here at 5 and become here at 6, which is, you know, what you ideally would expect, and it's cannot get more than T saturation. Then he come into that section and he start exchanging heat with this. So they stuck with the terminal temperature difference definition, which is what is the exit temperature compared to T saturation of the steam. So because of that definition, you look at the chart, and when you look at the big chart of a power plant, you will see TTT numbers. And you see like it's 3, 2, 3, and then 0, and then -5 and -7 in the big guys. What big guys? The guys that are pulling the high pressure one, the one that is pulling from very high steam. So they are pulling from superheated steam from the high pressure turbine or the intermediate pressure turbine. So those guys could have a negative temperature difference. Okay? No, terminal temperature difference. Because you can see how it's like the end of the process, kind of. When the steam finish, here's the diagram. He finished his job, no matter where he came from, whether he came from here or here, but he finished his job here. He finished always, remember this for today too. He finished always at T saturation. And the water that you are heating from say 5 to 6, you look at the difference between them, and that difference is terminal temperature difference. Okay? If you are above it, you are B negative. Make sense? If 6 end up being here, rather than here, if 6 is here, you have 0 terminal temperature difference. But you are above this, and that's because this guy is heating you at that stage, so you can go up, then you have negative. Make sense? No?
Still there. So it's got to be, so you're superheated, then you got to go through a D superheated.
Right. It's basically, they are saying that we just don't dump the steam in a big tank. No, there is a pass, and we have few lecture on heat exchanger. So we're gonna discuss this. But point is, they are doing this arrangement basically, where the steam do this, while the cooling water is doing this, or the feed water. So while the feed water is trying to heat, it's going in counterflow arrangement with the steam that is doing this. So in that part, and we call this part the desuperheater, very hot steam is used to heat the water. So the water not only can reach this point, the water can even go a little bit higher. Right? And by the way, this part, what do you think a good name for it? If this is the desuperheater for the steam, this will be the last part, huh? Before they pull the steam and throw it to the next feed water heater. Free quiz if you have a good name for it. Huh? De-liquefier. It starts with a D, but not liquefier, no. But you are close to the logic. Start with a D and it has to do with liquid. D what? Dehumidifier? No, there is no. Humidification is like when you have air water. This is all just water. They call it, no, drain cooler. Drain cooler. So the drain, let's cool it a little bit more. So not only are saturated, but we can subcool it. Why? Because we can. Because the water is actually way colder than him. So let's not throw him as saturated steam. Let's cool him a little bit more. So the big heat exchanger is 3 parts. Desuperheater, the main part where he actually condense, and then the last part, the drain cooler. And they can do this. Why? Because the water is doing counterflow. So every section, the water is here for you to take the heat from you. It's always cooler than you. Right? Having said that, that drain cooler will complicate today's quiz. So in today's quiz, any feed water heater will finish saturated. If it's closed, we just drain it backward. If it's open, it leaves together with the water. See, that's an open feed water heater, guys. Okay? They all meet at saturated point and you pump it up to the next level, next pressure. Make sense? So here is the turbine. Extracting. First one, that's a closed feed water heater, pump it backward. That's the second feed water heater, pump it backward. And then this is the third one, open feed water heater. How? Because I see he's saturated at the end and he's getting bumped up to the boiler pressure. Make sense? The bottom of what? This? That's the condenser, right? Then we have to put the condenser. Huh? This guy is open, right? How could I tell? Because he leave here, right, as saturated. And it has two inlets. You got steam from here, you got steam backward on him. And of course, the water is into the tank. So if we draw it, it will be water like this, steam coming from here, and steam coming from the other side. And everything is leaving in a big pump. Make sense? Good. So the equation to calculate the steam required for open or closed feed water heater is the same equation. And that equation is the first law in this guy. What's the first law in this guy? You would say energy in equal energy out. So here I got M2H2 plus M dot 1 minus M dot 2 H5 equal M dot 1 H6. That's what you're looking at over here, right? And in this equation, there is only, if you know M dot 1, then the only unknown is M dot 2. If you don't know M dot 1, then you can think of this equation as a way to get the ratio, M dot 2 over M dot 1. And most of the time, you just need the ratio. You don't really need to know what's M dot 1. But you're going to get M dot 1 later on from the work net when saying the pump need, the plant need to generate 512. That's how you're going to get your M dot 1. Okay, so here is the work. It's like two turbine minus 2 pumps. And notice how each pump has its own M dot. So that first pump is only having M dot 1 minus M dot 2, and the second one is handling the M dot 1. Right? Because you should write the M dot in the cycle. So this is M dot 2, and this is M dot 1 minus M dot 2. So again, those equations were there in the lecture notes. You just have to grab them and write them. And you get your M dot 1. All right? And you get eta thermal from work over Q added. Okay. So task 3, last project, and the next project is a simple cycle calculation. Okay, and in the second project, all of them are just a simple vapor compression. So VH cycle is the best, right? And it's like this. This is isentropic. So this is what? Constant enthalpy, throttling, constant pressure heat addition, isentropic compression, right? Constant pressure heat rejection, right? You need all the H's, 1, 2, 3, 4, and you'll be able to calculate the COP. And he's asking you to, well, try this with different refrigerants. So different refrigerant will have different, pH diagram. So the number will be a little bit different. But what should we maintain? Like I'm telling you, I want you to refrigerate this classroom with ammonia, with R134A, and with propane. What is, when I'm switching the refrigerant?
Same pressure.
Same pressure? No, not the same pressure. Same. It's not the same pressure, then same what?
H.
No, not same H. Same temperature. What matter is, I know this is pH diagram, but what really matter is what is the temperature corresponding to this and to this. This what need to remain constant. And how do we get this? Well, what's the temperature of your classroom? You want it to be 70 degrees Fahrenheit in the classroom, then we gonna design that refrigerant to come to you at 60 degrees Fahrenheit. And how hot is it outside? It's 90 degrees right now. Okay, so you're gonna stay, this is 90 degrees. So when I'm extending the line like this, I don't really mean that this is constant temperature. You guys know that the constant temperature line does not extend like that. It's only in the dome when the temperature and pressure are synonymous to each other, but outside the pressure constant, the temperature go like this, right? Completely different. So I'm saying 90, then this, we're gonna design this to come to you at 100 degrees Fahrenheit. Why hotter? Because I'm gonna throw my heat into the ambient. I need to be hotter than him. When I'm gonna dump my Q hot, I need to be hotter than him. And when I'm gonna suck Q dot L from you, I need to be lower than you. So the refrigerant, ammonia, R134, propane, need to have those temperatures. But because he's different dome, he will run at different pressure. So when we switch from, you know, R22 in the 80s, when we used them to R134, we expect different pressures. But we don't expect our house to get hotter just because we change the refrigerants, right? The COP, which will depend on the H, right? Those H value, remember COP for refrigeration cycle is what? Q dot L over work compressor. Those H value will be different for different dome, right? The COP will be different, right? So the H will be different, the pressure will be different, but you need to keep the temperature the same. Make sense? All right. So now in task 4, he said, now pick one of those guys, just one. You pick one. And I remember clear in the class, I said, just pick any one of them. You should pick the easiest, I would think. But in the second project, don't pick any one of them. In the second project now, we need to go one step forward, which is let's pick the best one from the preliminary design. So the one that sounds most promising for you, you move forward with him. Okay? You'd say that's the one that I'm gonna optimize. So write a MATLAB model of the cycle, tabulate the thermal efficiency versus the design parameter. What's the design parameter? The knob in my hand. In that design, there was only one knob. And that knob was the pressure of the supercritical pressure or the pressure of the preheater stage or the pressure of the feed water heater. That's the knob. And we are trying to figure out what setting is best. Okay? And you want to plot the variation of the cycle efficiency with the design parameter. As you play with that knob, you are trying to see what happened to the efficiency. Okay. So we're gonna do the easiest way to optimize the cycle, which is what? I mean, let's pick the easiest one, just supercritical pressure. And you want to figure out which one is best. What should I do? Repeat the calculation, do comprehensive search. Keep playing with the pressure, look at the best number, right? And I can afford this. Why? Because this cycle, and this is the program. I should post this for you so that in case you didn't manage to do it. It's simply calculating the H's from X team, calculating the work of each one of them, and then calculate the efficiency, and then plotting it. And I sent you this already, right? And so it will look like this. Here is the efficiency, and I'm also plotting the X. Why I'm plotting the X? Because I put it in part of my constraint when I was solving this. I said that this should be a cap on my X2. How wet is the turbine exit is a big deal. So the red is the quality, and the blue is the efficiency. Done by just let's try every single pressure we can put our hand on. Okay. So looking at this, if I don't care about the quality, if there was no constraint, it would be this. This is the point. Maximum point here is pressure 350. Okay. And the efficiency is 0.46, 46%. That's pretty cool, actually. 46% for a thermal power plant. But of course, this is, and when you plot this, it will be this point. So that is the temperature, the 1000 Fahrenheit, okay? And the pressure he's saying, you know, the 350 bar, 350 bar, which is 35 megapascal, will be this. So that is, I mean, we need to plot the cycle to continue like this. Will be here, and then this is the isotropic expansion to 50 degree or something, right? And then you go all the way to the blue line. The blue line, which is all the subcooled region is in this blue line, between the blue and the red, and you go up like this. Okay, so that is, so a few things that are actually striking here. One is that when you calculate that m dot from here, so I calculate m dot from the program, and we can run it. This symbol this is the temperature that Jenks power plant work at. Okay, and we are predicting the flow rate from the symbol cycle to be 2.9. Okay, 2.9 million pound per hour. That's very close again to real life. The one that they did after optimizing with 7 feed water heater. So what is, again, you need to be stuck in your head is that simple calculation, simple model are very fast to get you very close to the order of magnitude, right? If someone say, we need to build a truck running on solar panel, no batteries, forget about Elon Musk, we will beat him. We will just like coat our truck with solar panel and we will make the truck super cheap. No batteries. You can, in like 2 minutes, figure out that this is impossible. How are you going to do this? Well, what is the power? What's the horsepower required for a truck, a decent truck? And you multiply this by 736 to get into watt. And then each panel that you buy from Lowe's is like 300 watt. You divide the number of watt required divided by the number of panels. You will figure out, well, I need 50 panels. I'm going to stack 50 panels on top of the truck. Unless we're going to make them up, like vertically up or something. So the solution is, no, we cannot really harvest the energy on demand. We probably need to put those in your house, store energy all day long into your battery, and then get the battery into the truck. Right? So, where is P1? Yes. Okay, I need to run Xteam first. One. Yeah. And then run this guy. Like this. Right. So this graph is the m dot. Okay, and you can see that at 350 bar, which is like this, 350 bar would be here, and it's like 2.9 million pound per hour. See the 10 to the power 6. So I want you to have this in your head when you do the capstone next year. Okay, I don't want you to, a lot of students come to my office, so I don't do senior design, but they tell them go and talk to other professor to get more information about what you're designing. And they come with, I mean, first time they're gonna touch the paper with their pencil, and they wanna include every single detail of the design. That's not the way to go. You need this kind of skeleton draft of your design. Something that have the beef, the important part. Okay, turbine compressor, right? The important part, all ideal, all perfect heat transfer, right? And you will be able to say, based on those 3 design, that truck will run with solar panel, or no, we need battery. The power plant, we can run this power plant you know, with like, does it make sense to go supercritical or not? That show you, yeah, there is a point of going supercritical, but maybe the constraint tell you that you cannot run at 0.55 quality, man. You are gonna kill your return. So maybe you should cap it at 0.85. And so if you're gonna cap it at 0.85, the best efficiency you should dream of is 40%. Going any farther, that doesn't work this way. You have to do other stuff. Okay? So remember that simple design work, and that's why we need task 3. We will keep asking you to do it. And there was one more thing I wanted to talk about. Yes, the final answer. So when I get this, you know, and I'm calculating the numbers, I can just putting it on the TS diagram and just going like this, I can see the quality at the exit. So this cycle having a quality of 0.55 or like, sorry, 0.65 at the maximum thingy, then I can come here and check, is the quality really 0.65? Yes, it is. I can confirm that my solution is right. Why I'm saying this? Because a lot of time, students email and say, can you check if the solution is right or wrong? And this is important because when I was undergrad myself, I always thought that wouldn't it be great if they give us the homework problem with the actual number for the final answer so that we can check on our solution rather than spending hours trying to figure out if we are right or wrong. And I was determined if I ever become a professor, that would be the first thing that I'm going to do. Anytime you give a student an assignment, you have to tell him, calculate the compressor work. And it should be 40. The final answer is 40 horsepower. So that when he does not the solution, just give me the final answer. I said that would be great. That would be very educational until I graduated. And my first job, I was like assigned, I went to directly to grad school. And so first course I was teaching, and the professor handed me the problem sheet, 10 problems. And in that institution, the professor will have 1.5 hour lecture, and the TA will have like 1.5 hour problem session. So the professor don't do problem. He just like explain theory, draw graph sketches, but then the TA come and actually solve problems. And he gave me 10 problems and he said, we'll solve those 10 problems for them. And my response was, okay, where is the solution? And he said, what solution? You are a TA now, you know everything, go. And it turned out they don't have solution. And I'm supposed to come up with a solution, and I'm supposed to be confident enough. And when you think about it, in any job, imagine you graduated from here and you went for work for John Zane, and the first day in the job, they told you, we need to calculate the heat transfer area needed in that new heat exchanger we are building. And you're gonna tell your boss, yeah, I know how to do this, but can you give me the final answer? You will get fired. What do you mean you get the final answer? You are supposed to come up with a final answer. Your job is to come to the final answer. So I know you are not graduated yet, and we are still training to be actual engineers, but part of that training is when you give a number, when you calculate a number, you can check on the sanity of that number. There is ways to make sure, is it the same order of magnitude? Am I willing to bet my reputation and my job on that number or not? And I'm not asking you to bet your career or degree or the course grade. All I'm asking you to bet on is the 25% of your course, because that's what will take you from 3 to 4, that you have the final answer right. So it's not much, and you need to slowly come up with this skill, how you can trust the answer. Okay, can you work the problem backward, for example? Can you check it against what is available in real life? Like, for example, if we were just calculating the m dot, You know, I will go to an actual power plant and see what number do they have. Is it the same order of magnitude or way off? Right? So that's why don't ever expect me or the TA to tell you, yes, the answer was correct. But of course, we can tell you this is the right equation for sure. Or this, yes, you can assume adiabatic. We can help in the solution, but I want you to be able to look at the number in the eye and say, this is a good number. I'm gonna spend 25% of my grade on that number. That makes sense to me. All right? All right, very good. Finally, the last part is task 5, and that is quantitatively check your assumption. What does this word mean? With numbers. So when all your task 5 is, I feel the assumption is correct, or I am worried that the isentropic expansion is not really true. Feeling and think and I doubt, that's not good. And we just wanted one, not all of them. In the capstone, they want you to check all your design constraint and your design assumption to see if they are valid or not. But here I just wanted, and still in the second project, I just want you to pick one of the assumption and say, is it a big deal or not? What is a big deal? For example, isentropic turbine. It's not isentropic. It should be adiabatic only with isentropic efficiency of Google. What's the typical number? 85%. Okay, you recalculate what is the work turbine when it's 85%. That's a simple calculation. And then you would say, now look at my answer from the efficiency. It changed by this much. And I don't want you to recalculate everything. I just want you at this stage to basically just say, that is safe. It's not a big deal. Or wow, look at the difference this made. This made 85% difference or 50%. That is super big. I cannot trust this design. Someone else, not me, someone else need to revisit that design. But we need calculation. We need you to run the number to say, I neglected, like for example, a lot in 4000, in 4263 energy conversion, all the analysis, they completely neglect the pump. Forget like different power plants. The whole course is about power plants. Geothermal, nuclear, wave driven, all those, most of the time they neglect the power of the pump. So in something like this, you would say, well, let me check on that. What is the actual pump power? And then you would say, wow, it's like 5%. So you know what's 5% between friends? I'm okay. But if it's like 20%, no, that's not okay between friends. 20% is a big deal between friends. Okay, friends break at 10%. If you are above 10%, you're not my friend anymore. You need to be 10% or less. Okay. So any question about the project, how we are grading, any complaint that's fair, harsh, not fair, not clear, complicated? I think it's really, the professor who came up with that scheme, they really have a point. You know, the structure, they are preparing you for capstone, where you have to add stuff, where you have to start preliminary calculation, then refine the calculation, then check on the weakest link, basically, in your assumption. Okay, let's take a 15 minutes break and we will start chapter 12 after this.
You look like everything. You look fancy. 60 something. I know.
All right, I think we should start. Guys online, can you please confirm you can hear me? Yes. Right. Good. So. So we're gonna go today to psychometric application. So this is one of the most application of refrigeration and heat pumps. So when you think, what did we study in the previous chapter? It was basically that pH diagram, okay, and how does a compressor between the two reservoir is capable of taking the fluid, the working fluid from the low all the way to the high. Now your entrance could be the low place, that's when you have a fridge or a refrigeration, or your entrance could be the TH, the hot place when you are in a heat pump application or heating, okay? So one of the application that require cooling and heating all the time is air conditioning, right? And air conditioning is not just the temperature, okay? It's also the humidity in the air. Actually, it's how much fresh air. So I remember when I was undergrad taking my first HVAC course, you know, the professor was telling us how if you don't have enough fresh air, no matter how cold the air is in the building, the customer will always complain that they cannot breathe. It's so hot. It's no matter how, so the humidity is actually a big deal. It's a big deal for us, right? And so to remove the humidity and to understand how the humidity get removed, we need to understand the humid air. What is humid air? Humid air is a mixture of two things, air and water vapor. We need to be able to understand that new mixture, right? Air actually is a mixture too, right? We know that air is O2 and nitrogen, and our dry air model is O2 plus 3.76 into, that's the number of mole. So when we are burning a fuel in dry air, like let's burn methane, then we are doing this, O2 plus 3.76 into. The other way to write this is, probably have seen it, when they say 0.21 O2 plus, I guess the rest, nitrogen. That's the other way to say I'm burning in air. Okay, so the air is oxygen plus 3.76 mole for every mole of O2. By mole, I mean the Avogadro's number of molecules. So basically, I'm saying for every oxygen molecule, there are 3.76 nitrogen molecules that are hanging together. Okay, so although air is already a mixture, but you never really think of air as a mixture, right? You always think of air as, when you open your thermo book, there is the table for air properties, not for O2 and N2. And you can come up with R for air, 2.87. And you can even find the molecular weight for air, right? 2897 or something. So, and you can find table for CB. So we have always dealt with air as a new fluid called air. And we didn't care what was the ingredient. Like you get a cake, you don't care what's inside the cake, eggs and sugar and flour and baking powder. You don't care, it's a cake. Here is a cake, here is the air. But now for the first time, we actually need to consider the two components of the mixture. Why? Because we are hoping to what? Separate one of them, right? So that's why we have to keep an eye on that. So that is what is going on in this chapter, right? Ideal gas mixture and psychrometric application. Psychrometric is different from psychometric. So psychro with the R, psychrometric, that's the air water vapor mixture. Psychometric, and we're gonna see it today homework. Today homework, you will be asked to calculate the psychometric combustion of C8H18 plus air, dry air. So he wants you to figure out what is the stuff that's coming here, the mole fraction and the mass fraction of the. So when he says psychometric combustion, it means complete combustion. What's complete combustion? Every C is burned as CO2. So how many CO2 do I need? 8, because there's C8. And every H is burned into H2O. So if I have C8H18, how many H2O do I need? Help? 9. And therefore, for this psychometric combustion, sorry, what I'm saying, psychometric, for this stoichiometric combustion, stoichiometric. For this stoichiometric combustion to happen, then how many O2 do I need? I need 8 plus 4.5, right? I need 12.5. 12.5 O2 plus 12.5 times 3.66 into are needed. That is the stoichiometric combustion of O2 of air with C8H18. And it will make 8 CO2 plus 9 H2O plus how many nitrogen? All the nitrogen that's here will come out. So it will be 12.5 multiplied by 3.76 into. This is what's going to leave in the stack, in the chimney. That's what's leaving. That is a mixture of gases, CO2 and H2O and N2, right? And if you burn stoichiometrically, if the combustion was stoichiometric, then there will be no O2 left. Sometimes there is O2 left because you are burning with a lot of oxygen, because you don't want to have any fuel left over. So you give as much oxygen, more than what you need. In jet engine, they give four times more air than what's needed, because they don't want the temperature to get so high and burn the turbine in the jet engine, for example. But we are not going to have this, right? So we will figure out how do we deal with mixture of gases, right? And of course, the application that we care about is this. That is how we are actually cooling this building. This cooling tower over here, sometimes he's on the top of the building, like in this cartoon, but sometimes it's actually, why? Yeah, give me my pencil. Okay, thank you. Sometimes it's on the top of the building, and sometimes it's under the kitchen side of the building. If you go to the second floor, the kitchen where I made my coffee right now, right? I always watch the too big condenser. Too big. It's basically cooling tower, really. That basically running all the time to cool the whole building is being cooled on this side. Okay, so this part, this guy, that's your heat pump / chiller. Okay, this is the guy that is running on the pH diagram, doing this. His compressor is basically doing this, moving the heat from here to here. Okay, most of the summer when we want to cool the building, that part, the cold part is here. That's the cold part. The cold water that it's called chilled water. That chilled water go and cool the building. Okay, the hot part, that is his condenser is what's going outside to be thrown in the atmosphere, in the cooling tower. Okay, so this gets thrown to the atmosphere, and this is the side that is absorbing the heat from the building. Okay, now, and they calculate those guys by what unit? You think, because it's a compressor, they calculate it in kilowatt or megawatt, or they calculate it in ton. So ton is the power unit that they use in refrigeration air conditioning. So that chiller, although it's like regular heat pump, like we have in our house, but because it's big, they always call it in. So a typical one would be, like a big one would be 70 ton, 40 ton, right? To take care of a building. Okay. So he is just a heat pump, running on this pH diagram cycle. So what he sent here is cold water, and what come back to him is hot water, because it absorbed the heat from every floor or every space, right? Sophisticated. If you have a fancy house, you will have like 2 different units so that you can handle it. You don't have to turn the whole house. Smaller house will have just 1 machine and everything is being air conditioned. But if you have big building or like big house, you can actually separate different places. So no one is upstairs. Why we are air conditioned upstairs? Let's all stay downstairs for today or something, right? So then you can see that he's just sending cold water and bringing back hot water. But what happened to this cold water is supposed to actually be this. This is called the AHU. AHU stands for air handling unit. And the air handling unit is the cold water that's coming from the chiller downstairs or upstairs, or whatever the chiller is basically coming like this and leaving like this. That's the cooling coil. But there are more things that need to be done here, which is we are cooling the air, yes, but we have to take out the water too. The return air, this is the air basically coming from the room, going back to the room. So if we just circulate the air like this, the water vapor will increase in the space. More and more it will increase, right? Until people cannot feel comfortable anymore. And we'll see what's comfortable in a minute. But so that's why you have to send some out and bring some new. And when you do this, the new one could come with even more humidity. If this was like a COVID hospital or COVID dedicated wing of a hospital, they will tell you, well, all the air needs to come out and you bring clean air for us, right? So when you bring hot air from the outside, that also changed the amount of water vapor that you need to remove. So that's why we care about those pictures, because water vapor is a big deal on the air handling units. It's not just cooling. So cooling without removing water is called sensible cooling. But cooling with removing the water vapor is called latent cooling. So there's sensible part, there's latent part. Part that involves just let's lower the temperature, and part of let's take out the water vapor in the space. Okay, so he's listing what's important in this chapter: mixtures. Okay, and we will understand what is humidity ratio, relative humidity, basically how we can characterize what happened to that air. How do you say this is good air, this is bad air, this needs to be done, what needs to be done to make bad air into good air? Okay. Very good. So first, the mixture part, and that's the first homework problem. To figure out what is the mole fraction and the mass fraction. Okay. So he's saying that if you have a mixture, bunch of stuff in that tank, in that duct, air, water vapor, for example, or CO2 and N2 and O2. They will have different mass. That's easy. Kilogram, just put them in scale. How many kilogram? Kilogram, that's MR. But then there's also the number of moles. And I have to confess that when I was maybe up till high school, I didn't understand what is the mole. I couldn't figure it out. And just telling me, well, it's just Avogadro's number. How many Avogadro's number you have? That didn't even make sense to me. Like, why? Who care about this Avogadro's number? And we care about the number of moles and the number. So what is the number of mole? You have 5 kilogram. The molecular weight, what's the molecular weight? The weight of 1 mole. That is the molecular weight. The unit of the molecular weight is kilogram per kilomole. If you have 1 kilomole, how many kilogram? So for example, for H2, the molecular weight is, for H is 1, for H2, the molecular weight is 2. For O2, it is, and I need you to remember 4 numbers for me. H2 is 2, O2 is 36, N2 is 28, and carbon is 12. That's the molecular weight. So obviously O is 16 and N is 14, right? What is what? O2 is 36. 32, I'm sorry. Yes, sorry. 32. 32, yes. Because 1 O is 16. Right. So this is the molecular weight, kilogram per kilomole, meaning that if you have 1 kilomole, you will have this kilogram. Okay. So what's Avogadro's number? 6.022 10 to the power 23. Avogadro's number. What is Avogadro's number? That is a cycle that I could never come out from it when I was in high school. They will tell you the Avogadro's number is number of molecules in one mole. And then what is the mole? It's the quantity that have Avogadro's number. And as I kept walking in the cycle, I was like, what in the hell is this? So here, so that's a little confession, right? So until high school, I was a confused soul, moving this world, not knowing what is Avogadro's number. So it's simply this: when you are burning carbon, you need oxygen to burn carbon to form CO2. What does this equation say? Say one molecule of C, here is one molecule of C, come with one molecule of O2, which happen to be like this, because we've got like one O bouncing together. When those guys join together, they will form this guy. And that is a CO2 molecule. Okay, you can do this with one of this guy, and make one of this guy. Or you can get 10 of those guys, 10 of this guy, and 10 of this guy. Or you can get 6.022 and 6.022, and you will come up with 6.022. Okay, so when the equations say CH4 require how many O2 to make CO2 plus 2H2O, well, I need how many O2? I need 1, and I need 1. That's 2. I need 2. So chemical reaction happen based on the number of moles. So when we are mixing them, you cannot just say, let's get 1 kilogram of CH4 and 1 kilogram of O2 and expect them to burn and form this. No, you need one molecule, but I'm not going to count one molecule. How can I get one molecule and one molecule? You get Avogadro's number. Still, how can I count 6.22, 10 to the power 23? Well, if you can get us, how much? 12 plus 4, that is, 12 plus 4 is, well, 16, right? If you get 16 of this guy, and you get, that's 16 kilograms, so that's 1 mole, and you get 2 O2, you get 2 mole of O2, which each one of them is 32 kilograms. And you can do this per second or per hour, like the pipe is sending carbon and oxygen, the reaction will happen. So we need the number of moles, because that's how reaction happens. It doesn't happen per kilogram, it happens per mole. Okay? So that solved the puzzle for me. Once I start learning combustion, then the mystery was over. All right. So in order to find the number of moles, it's as simple as how much mass, what's the molecular weight of your components. You figure out how many moles are there, right? So 5 kilogram divided by H2 is 2 kilogram per kilomole. It's 2.5 kilomole of H2. If you have 5, if someone hand you 5 kilogram, a bottle of 5 kilogram hydrogen, you know that is 2.5 kilomole. And you can calculate how many kilogram of oxygen we need for this guy to burn. Make sense? It did for me. Anyway, so now in a mixture where you have M1 and M2 and M3, and like just our homework, and you wanted to calculate the mass fraction, you divide the mass over the total mass. And the same thing for the mole fraction. Ni over n. Okay, so let me grab my homework here. Homework. Homework, where's homework? Homework. And this will be homework 3, and it's due next week. Right. Homework 3. Why don't I? Here it is. Here. Okay, share my screen. Resume. Share screen. Yes. Yes. Okay. So forget about the first problem. We'll talk about it later. But here is the second problem. Second problem, please find the mole fraction and the mass fraction. I guess I flipped the sign. It should be yi and xi. Of the different book flip them too, by the way. But I just need the mole fraction and the mass fraction. Of what? Of the product mixture of the following stoichiometric reaction of CH, C8, H18, and air. So this guy. So how do I calculate the mole fraction? 8 divided by 8 plus 9 plus 47. Right? The mole fraction for H2O, what is it? It's 9 divided by 8 plus 9 plus 47. Right? Now the mass fraction is a little bit complicated. Right? It involves calculating the molecular weight. So if I want and so that was in oxygen, by the way, it was not in nitrogen. So there was no, actually it was. All right. So if I want the mass fraction of CO2, you see it? CO2 plus 9H2O plus 12.5 times 3.76, which happen to be 47. So if I have 8 CO2 and 9 H2O and 47 N2, that is my mixture. And you want the mass fraction. Okay. So we said the mass fraction should be Xi. So X CO2, what is the mass fraction of CO2? Well, 8 over that's the mole fraction. I want the mass fraction. So I need not only how many moles are in that drawer. No, I want to know how much mass in that drawer. So how many kilograms is there? Not just 8 kilomole. I want to know how many kilograms sitting there. How many? So 8 multiplied by
The molecular weight.
of CO2, which happen to be 12 plus 32, which is what, 44? See, that is the kilogram sitting in that box. Divided by 8 times 44 plus 9 multiplied by 18 plus 47 multiplied by 28. That is the mass fraction. That's what I wrote in the problem, but the book say mole fraction is y, mass fraction is x. And we didn't say it, but the mole fraction is y. That's what the books say. Okay, and I'm telling you, some books actually flip them, so that's why it's confusing. But we just calculated right now what the mass fraction. This is the mass fraction. Okay, so you got it. It's the mass in this pocket, the CO2 place divided by the total mass in the mixture. Say that again. And you need this for each one. Yes, you need the mass fraction for H2O, same thing. And the mass fraction of N2. Okay. Yeah, that's the easiest thing. So if I have this mixture and I want to calculate the mole fraction, and our book call it Y. Y CO2 is how many mole in that place for CO2? 8 divided by total number of mole in the thingy. 8 plus 9 plus 47. That's the mole fraction. So here are two funny things that always crack me when I'm reading the final. So I usually create the final myself. And so when I'm solving those mass fraction or mole fraction thing, I never really finish the calculation. Because I don't need to. You are university students, do the numbers. So to my surprise, every year, a lot of students just leave it like this. They never punch the numbers. Do you think that we finished the problem here? The problem say calculate the mass fraction. I need the number, right? They don't calculate the number. I never give them 4. I just give them 3 because they didn't give me the number. So why? You know, just the fact that I didn't write it myself. I just don't have my calculator with me. You know, you guys do it. Continue all the way. Second mistake that they do is they look at this reactant on one side, product on the other side, and the problem say calculate the mass fraction of the product mixture. And they start dividing, like for example, CO2. They will say the mole fraction of CO2 is 8, and they divide over 8 plus 9 plus 12 plus 1 plus 12.5 plus 40.2. They think that everything is there. But the truth is only the product is there. Why? Because the product didn't show up until the reactant eat each other. You know, there is only product that don't exist at the same place. Right? So that is funny. Think. So only the product, not the reactant. I mean, I could ask you about the calculate the mole fraction of the reactant, but that would be just the reactant. What I'm trying to say is reactant and product don't exist, don't coexist. Make sense? Yes. It's so when you're calculating the mass fraction, and this is your mixture, we need to calculate the mass in that pocket, the CO2 pocket. What is the mass in that pocket, in that location, in that group? It's 8 multiplied by, tell me, multiply by the molecular weight of CO2. That is the molecular weight of H2O. Tell me what is the molecular weight of H2O? How much? It's 2 plus 16, so it's 18, right? So it's the molecular weight of each species. That's how we calculate the mass. Number of mole time, how many per mole, the molecular weight. Okay, good. Very good. So now sometimes we calculate the mixture molecular weight, just like why the molecular weight of air is 28.97 or something. How do we calculate the molecular weight of air? Air is O2 plus 3.76 N2. That's our air. Okay, let's calculate the molecular weight of air, of the mixture. It's sigma YI MI. Mole fraction of each species, this is species 1, this is species 2, multiplied by the molecular weight of each species. This is the same thing if you want to calculate CP. The CP of the air. How do you calculate that? Sigma YI CPI. It's kind of average, right? So if I want to calculate the molecular weight of oxygen, of air, I would say it's 1 divided by 4.76. What is 4.76? That's the total number of mole of that mixture. Multiply by 32 plus 3.76 over 4.76 multiply by 28. Okay? When you do this, that is sigma YIMR. That will tell you the molecular weight of the air. Can anyone do it quickly on his calculator? So that we confirmed ourselves we did it right. So 3.76 divided by 4.76 times 28 plus 32 divided by 4.76. 28.84. Right? Pretty close. Right? Notice that the actual air has a little bit other stuff too, right? Helium and neon and some other stuff. But this is how you calculate the mixture property, sigma ii mi. Okay. And so he's saying, well, here is those guys. This is my mixture. Calculate the molecular weight for me. By the way, the molar analysis mean the mole fraction. When he say 50% and 35%, 15%, he mean that is my mole fraction of each species, right? And you see is multiplied by 28, 44, and 32. Nitrogen, CO2, and O2. Make sense? Very good. So, of course, we know that B equal rho RT, right? Where R is the gas constant. R, the gas constant is what? R universal over M. And R universal is, how much is that? The 8315 over the molecular weight. So if you are wondering like why air has an R of 287, it's because of this. Why helium have different R? Because it's 8315 divided by 4 for helium, right? So you get the different number. Okay, so R universal is 8315 joule per kilomole. So people can write it like this, or they can take then R and M together, and they can turn R into, let's write this carefully. So we know that B is rho RT, which happen to be rho over R universal over the molecular weight T. And what is rho? Kilogram per meter cube. That's mass over volume. R universal MT. So what is M over capital M? We just did this one slide ago. What is that? Mass 5 kilogram divided by the molecular weight 2.5. N, right? The number of moles. So it's N VRT. So R universal. So you can say B equal rho RT, or you can say BV equal N RT. Okay. So if you use R universal, you use N, right? And you can say B equal rho RT. And when you go to grad school, you will say it's N KBT, where KB is Boltzmann constant. So this is all just like the same images, of the same thing, different images of the same thing. All right, so because of that format, here is a really important thing that we need to understand. That the pressure, I remember that the first time I actually understood what is pressure, and I was undergrad, it was my freshman year. I was fascinated, and I went back home, and my mom was there, no one was still home, and I told her, you have to listen to this, like, just figure out what is the pressure. And I kept explaining the analysis, and I remember she was like looking to the ceiling, and I'm explaining, I still remember that image, and it's like, she told me, you have to leave me, your sisters are coming, I didn't finish cooking yet, you have to leave me right now. And I'm like, no, hold on, this is like really cool, you need to listen to this. So what I was fascinated of is that I understood that pressure, and it was our first, like it was thermodynamics in freshman. I mean, the course was horrible, but that part was amazing, that you realize that what is the pressure? What is the pressure of a gas sitting in a tank? What is the unit of the pressure, by the way? This Pascal thing is Newton per meter square. What that tell you? Force over area. And why the force is coming from? Huh? No gravity, no. This is even, forget about gravity. If you will take this to the outer space, away from the Earth, that box will still have the same pressure because of the guys sitting inside. Where is the force coming from? I can't hear. Molecules bouncing back and forth. So what I was fascinating is that they calculated the pressure from the velocity of the molecule bouncing. So what is like groundbreaking for me at that moment is that I understood that if I have O2 and N2 in the tank, they could have O2 and N2, they could have different pressure. You and your friend are ganging on one bad guy and you are hitting him. Huh? But you are not as strong as your friend. So you kick like 2 kicks per minute, but your friend 10 kicks per minute. When this guy go down, it's your friend, not you. We can split the pressure. Huh? So when they sit in the same room, they can, we call this what? Partial pressure. And usually you give it the symbol, this like P with a single unit. Huh? And they basically say the partial pressure of O2 and the partial pressure of N2. What is that? You are splitting the kicking between each other, right? And when you look at this equation that we just wrote, you didn't write it yet. I mean, this will be in grad school. But the pressure and N, it's really how many guys are in the room. If you have so many molecules O2, they will kick more than the other, because simply it's pressure and N, number of molecules. Or what we, in our book right now, what we wrote here, BNI. Huh? P is NI, that's the number of moles. So PI is NI over VRT. So they cannot have different temperature. And you'll understand this clearly when you go to grad school and take my microflow course. I teach a graduate course called microflow, which like really deal with molecule on the molecular level behavior. But the point is, there is such only one temperature. And there is one volume that we share. But we can count how many are wearing red t-shirt and how many are wearing blue t-shirt. And those guys, because they are more, they kick more than those guys. And so they have different pressure. Okay? And it is really related. So we can actually realize immediately that, and this equation will be useful for many courses, is that BI is related to NI, just like B is related to N. So what is PI? The pressure of this particular species. What's P? Total pressure. What's NI? The number of mole of this particular species in the box. What's N? The total number. So then BI over B is simply YI. The mole fraction is your share of the pressure. So if you want to know what is your share of that total pressure, you just multiply B by YI. This is super important. And the partial pressure is really your pressure. Okay? You know, when we calculate the worst value of you and your brothers, and here is the value of the family, okay? You are Sam Walton and Rick Walton and whatever Walton. Well, yes, this is the Walton family and this is your wealth, but what is your share? So it's your account. How much it does really matter. So if you are not Sam Walton, but you are H2O in that air mixture, we need to know your partial pressure. We don't want the fact that you are sitting at room pressure in this classroom is not important. What's important for when you're gonna condense, when you're gonna fog, is not the atmospheric pressure in the room, is the pressure of H2O. Okay, so the water vapor in this room will start condensing based on his partial pressure, not the total pressure. Make sense? So when I was in grad student in Michigan, my roommate was so weird. He would, in the middle of the winter, he will just be in like summer clothes, and he will crank the heat all the way up. And he's like, why? And the funny part would be like, I would be coming from ice cold weather outside with my glasses. And the moment I go into our apartment, my glasses is totally white. And like, and his name was Jordan. I'm like, Jordan, what in the hell? He like, wear something and put the air and lower the temperature. Why we have to pay all this electricity to? Right? So that water vapor in that room condense based on his partial pressure in the room, and he's responding to my glasses temperature, which just came from the outside. Okay. Does this make sense? So BI is YI times the total pressure. Let's remember this. Okay. And of course, if we add all that small pressure components, we will eventually come up with the big pressure. Very good. Okay. So that's what I told you, like not just molecular weight. If you want to get any property, you can do it like this. CP, find the CV for each component and do the average this way. It's like a weighted average. How many? Then you would skew the average toward you. If YI is have big mole fraction, then the CV will go to that. And that's why the air molecular weight is not 31. The air molecular weight is 29 because it's mainly 80% almost is nitrogen. So that's why the mole fraction, the molecular weight of the air is almost like nitrogen. You go from 28 to 28.8. Right? Make sense? All right. So now this was general for any mixture. Now in HVAC application, we are particularly interested in just two guys. Dry air, that's a new species now, we call it dry air, which is O2 and 3.66 N2. Let's even forget about this composition from now on. We just have air. And the other guy is H2O. That is the mixture we are interested in. Okay, so dry air and water vapor. And we call this mixture moist air. We need to understand the property of that moist air. Okay, so the first thing is that the water vapor in the moist air has very small mole fraction. Okay, very small mole fraction. What that means when it comes to its pressure. If you have very small mole fraction, then your partial pressure would be very small. So while this room is sitting at 100 bar, 101.325 kilopascal, the share of water vapor of this is very tiny. So that case diagram that we have been plotting, when the pressure go to, you know, like 220 over here and 50 bar over here and 10 bar over here, it's not going to be even 1 bar. It's going to be very, very, we are here, guys. We are here, very low, and the temperature of the air is like, you know, 30 degrees C, 40 degrees C. So because it's very low, we meet far away from the saturation line. The water vapor in this room is really superheated. He's not liquid, of course. He's not wet. He's way over there. And when gases are way superheated, like oxygen, this oxygen in this room, can you consider as a liquid? No, it's not. But I said that they use liquid oxygen in the rocket engine, like the space shuttle was all liquid oxygen, and yeah, that's only when you go so the oxygen is like sitting here, way superheated in this room. To take him into a liquid, you need to take to very high pressure and lower the temperature so much. Then he can become liquid. Okay, but right now he's way superheated. That almost happened for the water vapor in this room, not because the temperature is too hot that he's sitting at 1000 Fahrenheit. He's far away from this line because his pressure is so low. Okay, his pressure is so low. So what that tell us then? Because he's so low, he behaved as if he's ideal gas. So the vapor that I think for most of your career so far, you were always told, don't ever use V equal rho RT for vapor. Instead, go ahead and do what? Use a steam table to figure out the relation between, pressure, nu and T. If you ever wanted to calculate the nu for steam, I would tell you go to steam table and get B and T. Like use B and T and get the volume, specific volume, right? That was always advice. Never ever use ideal gas for water vapor. Today is the day we break from this rule. Today is the day where you can actually use this for water vapor. Why? Because water vapor at psychrometric application is such at very low pressure that it is really behaving as if it is ideal gas. Okay, so he's gonna basically tell us how the vapor pressure is what the mole fraction of the water times the total pressure, right? And then he's basically saying we are way over there, huh? And because we are way over there, no, let's jump to the way over there. He is doing this. Look at that. The mass is basically following the ideal gas. Okay. How could he do this? Because the vapor is superheated. How is that possible? It's because the pressure is so low. Okay. Make sense? All right. So to deal with moist air, we have to define two important properties, phi and W. Omega, sure. I call it W. But let's call it omega. I don't know, I like to call it W. Let's call it omega. Because it really looks like omega, right? I mean, it looks like omega. Well, we will actually, let's see the psychrometric chart from Owen, because that's the one that we will use. So Owen chart. He actually didn't give it a symbol. He just said, give it the name. All right. Omega. Sure. So the first one is phi, and the second one is omega. And actually mixing those two guys mean that you don't have any idea about psychrometric. So last year or the year before, like in the whole problem, 15 people got the solution from check.com. And the guy in check.com didn't really understand what's phi and omega. He mixed them up. And so just based on this, that he used omega like W, I basically managed to convince the 15 people to sign that they did cheat. So every one of them signed, yes, we did cheat because we obviously didn't understand what's the difference between omega and W. So if you want to copy this homework this week, you need to understand what is omega and W, right? I'm kidding, no one copy. So what is omega so what's omega and phi? So phi is the relative humidity. And it's given as percentage. So you'd say 80% humid, 50% humid. Okay. And on a TS diagram, when the temperature is like this is the room temperature, let's say it's very hot day, 40 degrees C. Okay. This is the saturation pressure corresponding to the temperature in this room. The water vapor in this room could be, the water vapor in this room couldn't be higher than that vapor pressure to start with, because if he's higher than that water pressure, he will be intersecting with that temperature where here. If the pressure is higher than B saturation, it will be compressed liquid. So the maximum pressure for the water vapor to be in this room and still hang around with us rather than drop dead like water droplet is B saturation and lower. Make sense? So let's say he's here. Let's call this P gas. So he will be here, temperature 40 degrees, this P gas, way lower than B saturation. Okay? Well, phi is simply that ratio, B gas over B saturation. Saturation at what? At the temperature of the air. And so when you are 100%, you are basically here. You are sitting at that pressure. That is the maximum you can get. When the air is 100% humid, that means that if I sweat, there is no room for my water to leave. I will just move with my water around me. Nothing come out. Because why would the water leave? There is no room in the air. Right? So that is the relative humidity. All right? And how do we calculate phi? B gas over B saturation. All right? How do we calculate B saturation? Well, look at the steam table, find out for this temperature, what is B saturation? Okay. How do I calculate B gas? B vapor, which is B gas, is YI P. If you know the mole fraction, you should be able to calculate the vapor pressure, the part of that pressure that is belonging to the water. Make sense? Very good. So that's what you see over here. Right? And he's saying we cannot go beyond 100%. It's like 0, nothing, dry air, or 100%, the maximum you can afford. All right?
What would
Now,
0 on the chart look like?
What is 0 does not exist. 0 does not exist on this chart. The pressure is not there. Right? The limit does not exist. You remember that movie? The limit does not exist. So
would it not need to be 0 greater than 0 then? Not greater or equal to?
I mean, it could be greater than or equal. I mean, it could be 0. You could have dry air. I mean, if you have if you develop a dehumidification scheme that is perfect, you can generate dry air. So 0 does count, and 100% does count. It exists. But what I'm saying, it does not exist on the TS diagram, because there is no pressure for it to show. There is no air molecules. And vapor is 0. Right? Right?
Okay.
Good. So now the humidity, so this was the relative humidity phi. The humidity ratio omega is the mass. MV over M air. Kilogram per kilogram dry air. That part is very important. It's per dry air, because you would think it should be kind of like mass fraction. Shouldn't they do the mass of the vapor over the total mass? That would make sense. No, they do mass of the vapor over dry air. Why? in the HVAC application, they really do things per dry air. So it's really convenient for them to do it like this, just dry air. But that can cause a lot of problem for us solving problems. So let's remember, it's per dry air. And this is an equation to solve for omega. And it's coming from calculating the mass of vapor and air from ideal gas. And this should be a shock to you, shock of your life. What they are doing water vapor as ideal gas? Yes, they do. Why? Really, really superheated. Okay? Make sense? So if we want to calculate W, so omega, we can use this equation, 0.622 PV over P minus PV. And isn't this nice? Mother Nature is so kind to us. Avogadro's number is 6.022, 10 to the power minus 23, and this equation is 6.22. So you just have to remember 622 and you are all good. You get two numbers for free. Right? You don't have to remember anything. The exam and the quiz are all open, right? Very good. So before we continue to the next one, there's something called psychrometric chart that look like, I already posted for you online, and it looked like this. This is the one from Owen, our own Owen from Tulsa. So you should be really proud. Like, we have a chart that people use in the world. And this chart have on the y-axis, have a lot of things on y-axis, but the main one is the humidity ratio, pound of moisture per pound of dry air. Does this y-axis change if it's kilogram of water per kilogram of dry air? Do I have to do any conversion?
No, it's unit.
No, it doesn't. Dimensionless. So pound per pound, kilogram per kilogram, ounce per ounce, I don't care. It's the same number, right? But look at the numbers. What are those numbers? 0.008, 0.01. That is the mass, almost. It's not the mass ratio, right? Not the mass fraction, because again, it's not the total, it's the dry. But it's very close because 0.01 over, meaning if it's modified, you have to add over 1.01, right? You just have to add 0.01 to the denominator. But the point is so small, right? Mass fraction is so small. There is not that much kilogram of water that the air can carry. It's not that big. Very good. So that is the y-axis. Those curves over here, which finish by this last one, are the relative humidity. Okay. So when you look here, so this curve is 10%, 20%, 30%, 40%, 50%, Okay. Right? And I guess 0%, that is the dry air. So it starts from 0, 10, 20, all the way. So the last one is 100%. Okay? And it does not exist after that. And the x-axis on this graph is the temperature of the air. Let's call it now the dry pulp until I explain what is the wet pulp. Very good. So then this chart is really super easy to calculate things from. Like what? If I was given phi and the temperature and he want me to calculate omega, what do I do? He said phi is 40% and the temperature is like 30 degrees C. I go 30 degrees C or whatever there's also chart for the Fahrenheit. Right? And in our thermo book, there's two charts too. Right? There's one, I think, for SI and one for the. You can get them anyway. Super easy. So if you know the temperature, 30 degrees, and you know the phi is 40%, all you have to do is like go like this and read what is omega, and you're done. Temperature and phi, you get your omega. Now, if we're going to solve it by equations, why do we need to solve by equation? In case, so this chart was done for atmospheric pressure? What if this whole thing is not at atmospheric pressure? Vacuum, or like really high pressure tank or something. Then you need to use the equation, right? So using the equation is a little bit longer, but more accurate. So you think, well, I want W omega. Then it's 0.622 PV over B minus PV. What's P? What is that B without anything? Total pressure, the 101,325 Pascal in case it's atmospheric. Okay, now I want to get my BV. How do I get my BV? That's the pressure of the vapor. How do I get that? What do I have again? Phi and T. What is phi? B gas or B vapor over B saturation. Here, I got it. If only I have B saturation, because I have phi, if only I have B saturation, I'll be able to calculate my B vapor. How can I calculate B saturation? The temperature. So knowing the temperature, you go to the steam table, find out what is B saturation. Knowing that phi is 40% and B saturation, you calculate B vapor, and then you go to the equation, the 0.622. But see, the chart give it to you as basically a piece of cake. Okay? Make sense? Right? Good. So there is actually a MATLAB equivalence to this chart, and it's called, I also uploaded it for you, and probably you're going to use it at one point as a project. It's called psychometric new.m. So it's like XTeam, same deal. You have to call it, give it some stuff, ask for other stuff, okay? But what's nice about it, remember how in XTeam, if you want the H, you have to say XTeam and then open the quotation, say H underscore B and S. That means that I want the H term B and S. But if I want the quality, I have to say X underscore, B and T. Not B and T, it cannot work. X, it has to be like, yeah. So I have to change the call depending on what I want. This one, it's just one call for everything. Okay, so that is nice. But what is also annoying is, so it's the same deal for everything. So what if I want the omega and I have the pressure and the temperature, for example, the phi and the temperature, what should I do? So I guess I need to show you the code for it. Yes, this is a way to call it. So the matrix that you send in will have the thing that you want. So I want this and this and this. This is obviously the H and the wet bulb temperature. And the thing that I'm going to give you are, here is the temperature and here is my W. Okay, so what I'm saying is that, yes, this change, but it's kind of like what property I'm giving you, but the thing that you're going to send, it's just like one big matrix, and you tell them, I want this and this, but the other four, I don't need them. So that forces you to understand, well, what are the total 6 things that you can get? It's actually 7 things that you want to call for. See, for example, here, he's telling him, I have the temperature and the phi and the pressure, and I want you to calculate the W for me. Okay? You will get used to it. You will learn how to use it later on. But for now, we can use the chart manually, or we can use this equation together with this equation. All right? And let's have a 5-minute restroom break, and we'll start again. 5-minute restroom break. we will, let's spend 5 time or 10 minutes discussing it. Yes, there is. Let's ask me this again. Ask me, because this is important. All right, so we explained how this chart is really useful. We can solve the problem like this with it. Only bad thing is that it's only for atmospheric pressure, so maybe you need another one for lower pressure. Chances are we're just going to use atmospheric pressure, right? But we have this MATLAB code, psychometric chart new, which you can specify any pressure you want. And it's pretty good. Okay. So now one more thing missing in we need to understand this chart. So this is omega, what I like to call W. And this is the temperature of the air. And those lines are different phi. Okay. So a point like this, okay, there is, when you look at the chart, there's also those lines. And those lines are sitting on a scale like that. And those lines are constant H, enthalpy. Okay, so those are constant H. So to calculate the H of the mixture, you need H air plus H vapor. And because it's mixture, just like what we did in all those feed water heater, it's you add those two guys together and you try to calculate the H, it's mass fraction times H plus mass fraction times H. Why mass fraction, not mole fraction? Because the H, what's the unit of H? Joule per kilogram. So when things are per kilogram, you do mass fraction. When things are per kilomole, you do the mole fraction. So remember this in case you wanted to calculate CP of the mixture, and the table you are using has the CP in unit joule per kilogram Kelvin. Will this guy get multiplied by, you're trying to do sigma CPI, it get multiplied by XI. Why XI, not YI? Because it's per kilogram. Okay, so when we make things per kilogram, we multiply by the mass fraction. When we make things per mole, then mole fraction. Okay. And so then he, look at this. This is the H of the guys of the mixture. And then he divided by MA, not M total. He take this MA and put it on this side. This become the enthalpy per kilogram dry air. And it becomes simply H air plus W H vapor. So that H air plus W H vapor. So that's why in this chart, when you read what is this H, they will tell you it's kilojoule or BTU per kilogram dry air. Okay, it's per dry air, not for all air. So if I share here, share screen, this is the chart that I downloaded for you. Enthalpy BTU per pound of dry air. See all those lines going up, it's enthalpy per pound dry air. Okay. So, okay, that is line of dry air, fine. And then, so here's an example. We can do this using the chart in a minute. So he's giving us the temperature and the humidity, the relative humidity. So up 80 degree, cross the curve with 80, you find yourself. You can go and read W, omega, or you can go up on the line and read the enthalpy per dry air, right? And he said calculate this and this. So in the chart is a piece of cake, but what would be nice is actually to see the equation, how he's doing it by the equation, right? So, and then he's saying that he is having an electric heater or something. There is like an electric wire that end up making the air go from 10 to 30. Okay, and you want to figure out what would be the W omega at the exit and what would be the Q dot that is needed to do this job. So on the chart, how do we solve this? We started at 10 degree and let's say, what did we say? 80%. So let's imagine this is the 80% line. And so we are here at this point. And he said he's going to heat it all the way to 30 degrees. So when you are heating with electric wire, you are not adding steam or water. Are you going to go up or down or remain horizontal at the same W? Remain horizontal at the same W, because going up or down, it means that your W is increasing or decreasing. That means your relative humidity is either up or down. Sorry, the moisture content is up or down. So it's not, it's the same. It's the same kilogram vapor with same kilogram dry air, right? So all I need to find out is the 30 degree line and intersect with a horizontal line like this. That's the start and this is the end, right? And when he said, what is W2? I will tell him, well, W2 is the same as W1, and I will just read it to you from the chart, right? But the second part, when he said, calculate for me how much heat I need to send to actually make that air go from 10 to 30, I will immediately think about what? When someone tell you how much heat does it take to do from here to here, what equation come to mind? Continuity, energy, momentum, or energy equation? Energy equation. I will apply the first law of thermodynamics, which would say Q dot minus W dot equal to M dot delta H plus delta kinetic energy plus delta potential energy. Potential energy, forget about it. Kinetic energy, it's the same velocity more or less. It's nothing compared to the enthalpy change. It's simply going to be delta H. No work done. So his Q dot per M dot would be equal to delta H. If we're going to have this delta H kilojoule per kilogram dry air, then you better multiply it by M dot of what? Total M dot or only dry air? Dry air. So this will be M dot air. So we just need to calculate this Q dot that he wants. How much does the heater need to put? We just need to get this H2 minus H1 in kilojoule per kilogram dry air. How do I get that? From the chart. I will just read this number. I will go up like this and read this number. And I'm done. Okay? So different point, you can read their enthalpy. And the enthalpy, it's the total enthalpy, but it's written for convenience per kilogram of dry air. Okay? Yes? So he's saying to start with, you know how like W1 is the same as W2 because you're not adding water, right? And then, so this is what needs to be done to get it from the equation rather than from the chart. What do? We need to use the equation. How are we going to get my BV? I need my phi multiplied by B saturation. How am I going to get my B saturation? Go to 10 degrees C and read what is the B saturation. Make sense? Temperature give you B saturation, you multiply it by phi, and that tell you how much of that B saturation you are at. And that become your P vapor. You use the omega equation, and that will tell you the omega. Kilogram vapor per kilogram dry air. First law of thermodynamics, right? And this is just H total, right? This is H total and this is H total, right? The chart gives you that H total immediately. But if you're going to use the equation, Will I ever ask you to just use the equation? I mean, can I force you to just use the equation rather than the chart? I think most application really can be done by the chart, but I would still think it's really important to use it, learn the equation, because we may run into a scenario where the chart does not exist, right? Low pressure something, or we are trying to design something, and that design need the equation so that you can build a model and optimize it. So when he does use the equation, he split them. He take the air together, and then he use the vapor together, right? And it boils down to this: air plus vapor. And see, because he divide by m dot dry air, then he end up with the omega over here, right? And so dry air, there are tables for them to get the H, and even for dry air, sometimes you can just get away with CB delta T, right? Now, this part, this is actually very important and very confusing. How do I get the H vapor, the enthalpy of the vapor? Why it's confusing? Because remember that vapor is not this guy. It's not Hg that I can get from the temperature. Like you're saying that you're at 30 degrees C, get your Hg. No, that's not Hg. Where am I? I am here. Because that's my B vapor. Why that's my B vapor? Because that was my phi. And the phi was B vapor over Bg. That's Bg. Because I'm not 100%, I'm not here. So I am here. So how do I get this enthalpy? How do I get this enthalpy? Yes, we need two properties, right? Just like a steam table. We will know we need the pressure and we need the temperature, right? But just like we approximated the steam as ideal gas, he is basically saying that you can also think that this PV is the same as, sorry, not P. This H is the same as Hg. That is the same thing that we did here. If I ask you to calculate that enthalpy, if the liquid side, remember, we would say it's a very good approximation to use this one. This enthalpy, which you need two property for pressure and temperature, you can think of it as HF. Why? Those lines are so close. We saw in the TS diagram, those lines were on top of each other. Well, over here, well, those lines are not so close, but there is not that much big difference in enthalpy between them. Is it wrong to use two properties and get the enthalpy? No, of course it's more accurate, right? But the difference is very small. You will be surprisingly embarrassed how close it is. So he's basically saying, just get the at 10 and 30, get the H saturation, H gas, and you are very close. Okay, I would not use either of them. I will just go and use my psychometric chart. Okay, but this is basically how you can get it if you have to do the calculation. Make sense? To start with, I mean, look at this. Those two guys are multiplied by omega, and omega is 0.06. So I mean, even if this guy, and look at that difference, right? So we are talking about 20 plus 0.22. So what if you screw up the HV a little bit? It will be 20 plus 0.23. Okay, 0.24. What is 0.02 compared to 20? It's not 1%. It's 0.01%, right? So it's really small. So then just the other problem too is that the problem with What is the problem with my, I don't want to do this. I want to use my pressure and temperature. Here, why did we have to do this approximation? Table does not exist. When you look at the compressed liquid part of the sample book, just like one page, and everything is just like, there's not that many. So over here in the superheated, they will give you this part. They're not going to give you this part, right? But if I have my X team, I don't mind, let him go and get it for me, right? If I have the tool, of course I will calculate it. But if I am doing it in the quiz or the exam in the midterm, I will not find a table, superheated table at that region to give me the enthalpy in terms of that very low pressure. The superheated region does not have that low pressure. I mean, technically it is, but you just don't care about it. They are all the way up there. But they will give you this. The saturation line, of course, is given. That's important. Right? Did this help? Okay. So now the dew point. What is a dew point? So if we are here on the TS diagram, and say we are at this is B gas, right? And this is the B vapor, and this is the room temperature right now. Very hot temperature. But then at night, it gets cooler. This is TS diagram, of course. At night, it gets cooler. It got cooler to not just 30 degrees, but let's make it this temperature. And let's call this temperature 10 degrees C. Cold front coming from north, from Canada, and the temperature dropped all the way to 10. While we are cooling the air, what happened to omega? From noon, right now, or like whatever, until midnight, what happened to omega? We are cooling the air outside. Does the omega increase, decrease, or remain constant? Remain constant. We didn't spray water, we didn't take water out. So it cool at that pressure. So when you take the temperature to 30, you will be here. 20, you will be here. 10, you will be here. So now you are saturated. I lost my voice. The thing that, need batteries. So I became saturated, not because we added water or removed water, it's just because the temperature dropped on us, right? No batteries. I think I have batteries in them. Right. Boy Scouts, always be late. So when you go down to this temperature, now you are saturated. That's when fog starts show up, right? And what happens if you take the temperature even lower? Well, if you take the temperature lower, that air cannot handle that water content. So what will happen? You will move here. You'll move here, and some will end up being liquid. And those liquid will set on everything that's cold, they will set on. The car become wet, the grass become wet, right? You woke up in the middle of the night to take your dog, your puppy outside to to train him, and everything is wet. The grass is super wet because of that. So this point, when we were originally here, guys, this point is the dew point. Okay, that's the temperature where the water will start dropping from the air. So on the psychrometric chart, can anyone tell me where is that point? So if this is point 1, this was point 1 here, heating took us this way. Cooling, the air will take us which way? The other way. It will go like this. And see how we are cooling and heating at constant omega, right? So heating at constant omega, cooling at constant omega. This point, if you read this temperature, this is the dew point. So cooling at constant W or omega is also meaning synonymous with cooling at constant BV. So you know BV, you know W. So as long as W is the same, BV is the same. All right? Make sense? So again, if I know my temperature and I know my phi or I know my W, I can find my location here. And if I want to find my dew point, I just go all the way until I hit this 100% curve and find out what is the temperature. And that is the dew point. Good? Very good. So he's saying then once you get lower than the dew point, you will drop more and more water, right? And so the fact that you on a TS diagram over here, and this is actually related to the third part of the homework. The third problem in the homework. If I am here at that constant, this is BV, and this was BG, okay? And originally I was at this T1, but then you said you're gonna lower me not just to this T saturation, the dew point, D dew. No, you're gonna lower me to this. So I will come like this until here, and then I will move down here. So now this is BV1, but this is BV2, right? So dropping to BV2, what does that mean? You drop to a new W. W is BV. It's coin with two sides. If you know W, you know BV, right? So going from this pressure to that pressure, and I had to go because you told me just let's go to 10 degrees C. And that was lower than my T saturation. So dropping to that new pressure means that I drop to a lower W. And you can calculate the new W from the equation, but from the chart, how does this work? If you actually dropped less than dew point, let's say dew point minus another 5 degrees, then you are here, you end up here. You went like this to the dew point, and then you go on the 100% to this one. Now you can see how you end up with, this is 0.1, this is 0.2, this was the original omega, and this is the new omega. The difference between those two omegas are how much water you dropped. And this is how every single HVAC building or mesh system we have work. They want to drop W, they have to take the air from one, not just to the dew point, they have to go less than the dew point. And most of the time, this dew point is low and going less than the dew point. Why do they need to go less than the dew point? Because they want W minus W. They want to drop the kilogram, They want to drop the pound per pound kilogram. So they have to go to extremely low temperature. The air gets so cold so that they can drop the W. We cannot throw that cold air on the people in the classroom or in the mall. They will start sneezing. So what do we do? After we went through this, what do we do? Too cold for the people. What do we do, guys? We heat it again to a reasonable temperature. So that is really sad, right? So we started here with really big W1 and high temperature, and we cool to the dew point, and we cool even more. Why? Because we want to drop to this W2. Here is 1, here is 2, here is dew point. And after we cool to this, we heat again with electric heater or something so that we can be ready to send this to the people. Okay, so the HU will have a cooling coil, right? That take the air from 1 to 2, and then a heating coil that take you from 2 to 3. Does this sound like a waste? It does. And that's why the Department of Energy just this year, like maybe 2 weeks ago, I was in the review panel for their peer review, and they had they funded so many projects. Each project was like $750,000 to get out of this. They basically think this is insane. This journey is insane. Why do we have to go this way? So all the other, like all those proposals from different researchers and different companies are trying to say, no, we don't have to go this route. There's another way to come here. If you can come up with a cool idea like this, you can save a lot of energy. You become famous, and you can win that award from Baker Hughes, right? So where is the other route? By the way, this route, like I'm very passionate about it because when I was in Michigan, and it's really humid over there because of the lake effect. So they cool a lot. And what's funny is, it's funny and sad, that the heater would break in the middle of the summer. And so our labs become so cold in the middle of the summer. So outside it's like 90 degrees and very humid, and we go to our lab and this is very cold. And we have to wear extra layer of clothes when we go work in the labs. And this happened like multiple times. The heater would fail of the building. Okay, so what is the route rather than going this way? If we don't go this, if you don't want to reach your ear like this, you reach your ear like this. So rather than going this way, how do you suggest we should do? We should go this way. I mean, this sounds like reasonable cooling. Note that we learned in last chapter that cooling coil, how does this cooling coil work? How? He's doing this, right? This cooling coil is a evaporator of a heat pump. And we learned also last time that if you want to take it really low, you go like this. And what happened when you go like this? If you want to go bigger delta T, what happened? The COB, remember? Q dot L over work compressor, that part become less and less. So how do people, some people don't really want to go to that low. They don't want to go that low, right? This cooling is decent. You can do this. This is basically just like a cycle like this. But to go all the way to that temperature, you have to go very deep cooling, right? So think about how we can go this route. And you can just Google the Department of Energy funded research to see how much millions of dollars they spend on basically on those systems. We are still developing them.
Just to clarify, between 1 and 2 on the top side of that, the water vapor that's being used is that the water vapor that condenses from the soil drops and comes out the hole.
Yes, that water will drop like this. And if you are in a desert place, that water, you have to collect that water and give it to the garden or something, right? You cannot just let it drop from you. This water is very valuable. That also mechanism is how you can, a lot of people work on getting water from the air, by this, like they tell you, well, we can generate water just from the air by cooling the air. So if you have like a wind turbine or something, you can run a compression cycle and just get water vapor from the air. And if their place is like desperate for water, they are willing to pay that energy. I'm not hearing you clearly. Say that again. If you cool the water vapor, if you cool the air with anything and you let him drop his water, that would be that concept. Yes, but I'm not really sure what technology you are talking about. But okay, well, this is like very practical route to generate water from humid air. Okay, and Mother Nature does it, right? And if you just Google cooling, like there's like they build this big architecture that just without actual vapor compression cycle underneath, just waiting for the night to cool down and for the dew, and then they put like big sail and stuff, and then they can collect the water from it. All right. Okay, you guys are ready just for one more thing. We are running out of time. You can ask me after. So I explained what cooling will do. Cooling will take you like this. Okay. So now when you are heating, sorry, when you are injecting steam, you will go up like this. Injecting steam, will take you from here to here or here. I mean, you can also add enthalpy. So, but moving along the constant enthalpy line, if this is 0.1, this constant enthalpy line will happen when you put water vapor, like a piece of cloth, on your thermometer and you shake it in air. What will happen is some water will evaporate, taking the enthalpy from the air. So the air will get cooler. That's basically how we get cold, like our cooling mechanism ourselves. We put water vapor and the water vapor evaporate, taking the enthalpy from the air. But the mixture, water and air, remain as constant enthalpy. So that way of measuring temperature with a piece of cloth in is called, taking you up this temperature is called, so this is the D dry pulp temperature, this is the T wet pulp temperature. So obviously, if you are 100% air, if you are here, you don't have a wet pulp temperature, your temperature is the same. But if you are dry, and at T1, you can cool down to this temperature. Because there is room for you to take water vapor and cool yourself. That's called evaporative cooling. So simply, rather than putting a vapor compression, if the air coming is very dry, but very hot, if you just spray water in him, he will leave, it's called evaporative cooling. And all you need is just like a circulation fan, just like send the air through this. He will leave maybe humid, but he will be very colder. Make sense? So in the psychrometric chart, this is basically saying constant H total. You come from 1 and you finish at 2. And this is your wet bulb temperature. Okay, what's interesting is you can, knowing your wet bulb and the dry bulb, you can find where you are. So let's say you are 30 and 20. The wet bulb, T wet is 20 and T dry is 30. How do I find where I am? Meaning, what's my phi, what's my W, what's my H? You go at 20 and you go up like this, and then you come at constant H, and that would be your point. So knowing your dry bulb and the wet bulb, you can find where you are on the curve. Make sense? Yes? So that is the dry bulb and the wet bulb temperature part. Okay, and that's the thermometer that they put water in it and they shake it. Right? And that's finally the cyclometric chart. So now we explained everything on the cyclometric chart. The wet bulb, which also happened to be constant H. Okay, almost, practically speaking, it's the same. The dry bulb is the x-axis, right? And wet bulb line is those lines, constant H line. Okay, and he's explaining how you can find your dew point that's moving horizontally. How you can find the relative humidity, that's the curve. Okay, how you can find your insult, it's going up and reading on the scale. Okay, the wet bulb temperature, it's actually going at constant wet bulb or constant H, it's the same, and reading this temperature on the x-axis. There's also lines here that is constant specific volume. Why do you need the specific volume? Because you need the density. Because sometimes you need to switch between flow rate. The HVAC people always love to use CFM. You always hear them saying cubic feet per minute, cubic feet per minute. But the first law, when we calculate the Q dot, we like to use M dot. We want to use M dot delta H. So we need to switch between the CFM that is so popular with engineers and the M dot that is so popular or required by the first law. And that's why you need the specific volume. And you will get it from the chart. Okay? And so here's an example. I tell you, well, determine the relative humidity ratio, and the mixture insult in kilojoule per kilogram dry air by using the dry bulb and wet bulb of 30 or 25. That's the example that I just said. Right? So he's saying, well, go for the 30 and the 25. Look, he's going up to 25 until he hit 100%, and then going at, you understand, constant H until he strike here between dry and wet. Wet is lower than dry because there is room for the air to get more water and cool down when he does this. Okay? So now, remember the cooling tower? We talked about the cooling tower last time and how the cooling tower can lower the temperature of the water. And we said, I told you how much he can cool you down. He can cool you down not just to the dry bulb temperature. He can cool you down to the wet bulb temperature. So if the air have room to get more water vapor, he can drop you to the wet bulb temperature. That's what you lose when you say, I don't want to lose any water in this cooling tower. I'm going to make it a closed system water cooling tower. I'm just going to turn it into a radiator in a car. Then your dream is the dry bulb temperature. You cannot go to the wet bulb temperature. The only way to go to the wet bulb temperature is that if you put water in the air and lower the temperature. Right? Very good. Okay, so I know that you want to do your quiz, and actually it's available right now. So let's look at the quiz together. So the quiz, where are we? Let me share here. So you find the quiz under assignment. If you click under assignment and then go to quiz 4, right, you will see that he has first 20% for saying whether you are attending in Zoom or you're attending live in the class. And if you are in the class, you have to write what's your seat number, right? Now 80% is, I just want you to plot this on a TS diagram. And you want to mark state 1 to 16. Where's 1? 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 16. I want you to put where they are. And basically, see the open feed water heater, how we talked about the open feed water heater that you need to meet, and the closed feed water heater with the thing cascaded backward. I just want you to put those pressure, label the points. So make a big TS diagram and start with high pressure turbine, and low pressure turbine, the condenser. Actually, you have start with the boiler pressure and the condenser pressure. And in between them, you're gonna put 1, 2, 3, 4, 3 pressure line, right? Those 4 pressure line are pulling from the turbine expansion. Just make it isotropic expansion. Pull 4 line and then work the end like what we discussed earlier today. Close 1, finish at saturated and cascaded backward. Open 1, pull the pump liquid, and they all go to the next pump pressure. Remember? Yes. So it's important to put the points in the curve. No, don't write what's given and what's required in that quiz. So it's 80. The reason why I made it 80% so that the TA can have easy time. So 16.80%, he's just going to give you 1 point for every point right. 0.5 points, so that he can collect his 8 points this way. No given, no required, just the curve, the TS diagram, and points sitting in the right place. What do you mean label the temperature? I don't have numbers here. Yeah, but I mean, start with 587 so that you can put it in the right place. It's important to see where is this 508.7 megapascal. Did you notice how the pump entrance is different from the pump outlet? Sorry, the boiler. Boiler is the flow is coming at 9.3 and leaving at 8.7. That means some kind of pressure drop in the boiler because it's like long network of pipes. So the line, like make it by such that there is a pressure drop. So let it come at 1, but then leave at a little bit lower pressure. I don't know about you, but I used to feel very good when I plot those TS diagrams when I was a student. I thought they were so pretty, you know? So I'm giving you a chance to enjoy it, just like I did when I was under.
So last week,
Yes, it's very important to submit before 8:30. Time is very crucial. That's a very important lesson. Zero tolerance for late submission. I have a proposal myself in 2 days, and if I don't submit by the due date and time, they will not let me. So we could lose $250,000 just by not respecting the deadline. You need to learn that lesson. 8:30 means 8:30, not 8:31. I hear you. Well, fortunately, we have 2 quizzes that we can forget at the end of the year. So that quiz is not going to affect your grade in any way. I'm going to waive 2 lowest quizzes for you at the end of the year and 2 lowest homework problems. 2 lowest homework, really.
We just choose the pressures of this.
So the question is, should we choose the pressure for different guys? So the optimum pressure is the one that will, we said that last time. We do what? We'll set the temperature equal spaced. So in the sketch, try to make them equal spaced. Right? Temperature equally spaced. So from the boiler to the condenser, slice them into different parts, equal parts. You understand, right? If the boiler is here, condenser is here, on the case diagram, just like take 3 parts that are the same and put the 4 pressures. We have a question on the chat. It says, on this, we have state 1 going into the boiler, not into the high pressure turbine. We will just call 1 here. Yeah, we can start with this one. We actually have to stick to those numbers. So if 1 is the inlet to the boiler, you have to put it in the inlet of the boiler. You cannot change the numbers. That's correct. Good points, yes. That is correct. That was Brady. Thank you, Brady. Say that again.
It's gonna be shit.
Always use pens. You don't use pencils. White House. That's White House.
Please don't forget to sign the pledge. Next to your name, write, I didn't copy, I didn't help others to copy the solution. Just a second. Say, sorry, can you repeat that about the pledge? I said, next to your name, please write, I didn't copy, I didn't help others to copy the solution. Next to your name. Questions? Can we put the pledge at the bottom? Sure. Bottom, side, top, wherever you have space. But the T is not gonna grade unless you see that pledge. Yes, you need to write, I did not copy and I didn't help others to copy, and then you sign. All right, I think every one of you has his own laptop, so I can disconnect mine.